Hi everyone. I would like to welcome you to this presentation titled HPC and Heterogeneous Architectures with OneAPI. My name is Amarpal Kapoor, and I'm the lead technical consulting engineer for OneAPI Cluster Tools. I have been with Intel for the last 6 years or so. And my principal focus area is HPC cluster tools, as well as the related technologies. Much of what we do is work with internal and external customers over co-design, co-development, porting, and optimization projects. If there are any questions post or during my presentation, please drop me a note to the email address that is shown here. Yeah, so that's the email address. And with that introduction, let me get started. So the agenda for today's presentation, which is supposed to last around 60 minutes or so, is outlined here. So I would start off with an introduction to OneAPI along with some motivations. Then we would look at the OneAPI toolkits that we have and the tools within the toolkits. I would then demonstrate a case study. This is a 2D heat conduction solver based on finite differences. So here you'll see how the toolkits come into play. And then I would also, on a real terminal, show you how these things work in reality. So the demo follows the case study. Right. So on this slide, which is slide number 3, I present to you the motivation of OneAPI. So here, if you look at the figure on the right side, we do have, in today's computing era, we do have quite a few diverse workloads. Here they're shown to be scalar, vector, spatial, and matrix. And think of them to be the various workloads you might encounter in your scientific and numerical computing on the HPC side, or let's say the various AI workloads, ML and DL workloads that you have on the AI side, or it might be other domains, for example, 5G and things alike. Now, each of these workloads have a certain programming model on which they thrive. Rather, I must say, a certain hardware on which they perform the best. And on each of these hardware, you need a separate programming model. So like is shown here, there is a different programming model for, let's say, CPUs, GPUs, FPGAs, and then the other accelerators. And things like the Movidia stick and other accelerators come into this fourth category. So the important point to note here is that there are a bunch of programming models that one needs to use in order to be able to and deploy their application on the various hardware. Now, this is not a trivial task. And sometimes the choice of a certain hardware is also based on this particular fact, that is, familiarity and experience with a certain programming model more than what really the workload demands. So in order to make the situation better, OneAPI came into being. And like you see here, what OneAPI does is it provides a common unified programming model for the various hardware that are of interest to us today, precisely CPUs, GPUs, FPGAs, and the other accelerators. Right. So in a single line, this is what OneAPI does. It simplifies life for let's say the developers who can now from a single code base target a bunch of architectures without having to reprogram for every architecture. So that's one point to carry away from the slide. And how was OneAPI realized? So two ways, and the first one is an industry initiative, and the second one is the accompanying product. So the OneAPI industry initiative is nothing but a set of specifications or standards for tools for direct programming, API-based programming, and mainly the libraries come in here, as well as the low-level hardware interface, for example, level 0. And these specifications are available publicly in this website that you see on screen, oneapi.io. This is a cross-industry, open standards-based unified programming model specification, and we are open for feedback. And if any of you would like to provide feedback, I would encourage you to please visit this website, and there is a way to provide feedback there. So please visit this page. And the latest version today is 1.1. And we do have a reference implementation for this set of specifications, and that is what is referred to as the Intel product here. So in here, there are a bunch of tools which are packaged into what are called as toolkits, and they adhere to the standards that have been laid out in the OneAPI spec. Right, and within this product are a bunch of toolkits. So starting off with what is called as the base toolkit, and then we have a bunch of domain-specific toolkits, and in here we have HPC toolkit, IoT toolkit for Internet of Things based applications, AI analytics toolkit, as well as a rendering toolkit. So the idea here is that everybody starts off with the base toolkit, and then based on their domain of interest, they would select one of these four toolkits to meet their computing needs. So that's how the toolkits are designed. I would walk you through the OneAPI based toolkit. So as mentioned, this would be the very first toolkit that people from any domain would install first on their system. And what is base toolkit? It's nothing but a collection of tools for direct programming, API-based programming, as well as analysis and debug. So things like compilers and interpreters, they appear here. So our DPC++ compiler compatibility tool, Intel distribution for Python. So these are the kinds of things that are packaged within the base toolkit. And then there are a bunch of around 7 to 8 libraries, like the math kernel library, or the collective communications library, or the deep neural network library. So based on the domain that you work in, you would find one or multiple of these libraries useful to you, and these are just a collection of thousands of APIs that encode commonly used functions in the various domains, and these are highly optimized for the best performance one can have. And traditionally, a lot of these are only supported on CPUs. But going forward in the OneAPI timeframe, they're all compatible to run on accelerators like GPUs, FPGAs, and more. And at the end of the day, performance is always something that one has to think about and tune for. And tools like vTune, Advisor, GDB are present to aid you with that within the base toolkit. Now, moving on, the next component that I also would like to share a few more details about from the base toolkit is the DPC++ compiler. So this is a high-level optimizing compiler. More than the compiler, it's a language to start with, right? So it is the DP++ language, which came about as an extension to the SYCL standard from the Khronos group. So this already existed, and Intel started off with filling in the gaps that it found within the SYCL specifications, and these were implemented as language extensions, and all of those came together and were called as DPC++. And then there is an accompanying compiler for the DPC++ language, and that is called as the DPC++ compiler. Right, and we also make use of well-proven LLVM compiler technologies in here, as well as Intel's own leadership in the compiler space. So this has been a new addition to the OneAPI toolkits when you really compare it with the Parallel Studio tools that existed in the past. So why would you consider using DPC++ compiler? Again, going back to the same message that we saw in one of the previous slides, and that is mainly a source that is written in DPC++ is able to eventually run on a variety of hardware, CPUs, GPUs, and FPGAs, and that's one of the reasons why one might consider coding their applications in this particular language. And broadly, these are SYCL codes, or these are legal C++ codes in the end. So at some point, these extensions we envision will become part of the current SYCL standard, and hopefully the C++ standards as well. So that's a quick note about our DPC++ language as well as the compiler. The next component that I would like to highlight from the base toolkit is the DPC++ compatibility tool. So what this compatibility tool is essentially a migration utility for CUDA developers. So for example, if you are a CUDA developer, or if you have a CUDA application that you would like to port to DPC++, then instead of doing that manually, what you might do is, you might run that through the DPC++ compatibility tool. And what it does is it migrates your code as much as possible to DPC++ / SYCL. And much of what we've seen so far is, up to 90 to 95% of the code is automatically converted, and things that are outside the scope of the compatibility tool are left to the developer to fulfill. And these are inserted as comments in the migrated code. And the developers are expected to go through such source files, do the changes that are needed, and at the end of it, a legal SYCL / DPC++ code is expected. Right, so that's the flow one can have with the compatibility tool. With that, I would move on to the next component, which is vTune Profiler. So if you have used our Parallel Studio tools in the past, then one of the commonly used profiling utility there was Profiler in addition to was vTune in addition to Advisor. So vTune gives a bunch of metrics that one can read and then suitably interpret, and could get good performance on CPUs. Today, the same has been extended to GPUs and FPGAs as well. So there are two specific analysis types which completely focus on GPUs, and the way one was using vTune for CPUs, you could continue to use it in the GPU based applications as well. So that is some quick notes about vTune, and moving on to the next one, that is Advisor. So Advisor, again, as you might recollect, has existed in our Paddle Studio tools since quite some time, and there are some GPU-specific enhancements that have been made into Advisor. The two important ones are the roofline analysis for GPUs, and then there is also what is called as offload Advisor. And we in our demo and the case study will see what this really looks like in reality. But at a very high level, Offload Advisor is a projection tool. Precisely speaking, it's a CPU-based projection, a compute-based projection tool. So what it really does is, given a CPU binary, it is able to project what performance that particular application might have on a target device. It could be, GPU. Various architectures of GPU are supported in the public versions that we have. And then without even having to really migrate your application, you would know if it is worthwhile to put in the effort in the first place. So that's mainly the benefit of Advisor. It does have a limitation that it doesn't project for communication kernels yet. So the focus currently with an Advisor or with an Offload Advisor is to be able to project for compute performance. And there are some nice utilities within Offload Advisor, or let's say functionalities within Offload Advisor, which is GPU to GPU modeling. Your start point could either be a CPU application, or it could be a lower generation GPU application. And if you would like to see what performance you might achieve on a hardware that doesn't exist, or maybe you don't have access to, that is something that one can also check through the Offload Advisor utility. So these were some of the highlights of the base toolkit that I was just sharing with you. And now we're moving on to the next toolkit, which is the Intel One API HPC toolkit. And on the figure here, you will see two different colors are mentioned, and the reason precisely is what I mentioned before. So the very first toolkit you should have is a base toolkit. So the light blue components come from the base toolkit, and on top of that, you would install the HPC toolkit. And the HPC toolkit will give you the classic C++ Fortran, as well as the new generation offload-based OpenMP offload-based Fortran and C compiler. Rather, C compiler is already covered, and the Fortran one is the introduction within the HPC toolkit. And then on the API-based programming, you have the Intel MPI library for multi-node support. And in the next slide, we'll see a few more details about that. And on the analysis side, Intel Inspector is an addition in this toolkit. So we saw Advisor as well as vTune in the previous base toolkit, and HPC toolkit introduces Inspector. And since we are mainly covering multi-node utilities in the HPC toolkit, we have a tuning tool called the Intel Trace Analyzer and Collector for tuning MPI applications. So that comes in here, along with the cluster checker to make sure that your cluster is free from any configuration related issues. Things like hardware dissimilarities, software dissimilarities are easily figured out through things like cluster checker. So that is a quick note on the One API HPC toolkit. And then one of the components that I just want to highlight is the Intel MPI library. And as you're aware, this library of ours has existed since quite some time. And it provides the best-in-class latencies and bandwidth when it comes to multi-node communications for large HPC applications. And so this is what existed even in the Parallel Studio timeframe, right? The newness here is that Intel MPI now is supported on GPU clusters as well. So the GPU cluster scenarios that we currently envision our scale up and scale out scenarios, that is multiple cards connected to the same node, and then multiple nodes with multiple cards, GPU cards each. So these kinds of scenarios are really well handled through the Intel MPI library. There is GPU buffer awareness that has been built in. And quite a few new features which are GPU specific are coming in. So please watch out for these as they get released in the upcoming OneAPI, MPI versions. Moving on here, I just, now we just covered an introduction of the various tools, and what I want to do here is just to show you how you can interact with these tools, and in a real life scenario, how they can be useful. So in this particular flow diagram, I'm assuming three kinds of customers or applications. And the first one is, you might have a CPU application that has been written in the past, and you're trying to see how OneAPI might be useful for you, or you might be starting the development of a new application today, or you might already have an existing CUDA application, right? Here the assumption is that you have, let's say, traditional C-based applications. So with that, let's see how the flow looks like. So assuming that you already have an application that works on the CPU, so the very first thing that in the context of OneAPI one would think about is, can I use accelerators for better performance? And so will offload be useful, right? And if you have enough experience with the application and you understand the architectural details of the hardware of interest pretty well, it is not difficult to answer this question. But let's say that doesn't exist, and then the way you answer this question is through the use of Offload Advisor that we just saw in one of the previous slides. At the end of it, after running Intel Advisor, and I would show you in the later part of this presentation how you would run Offload Advisor, you would know if there is a gain coming in from running this application on a certain accelerator or not. And so, it could either be a yes or a no gain versus, negative gains. And so let's assume that you see some positive gains. Then the next question you have to answer is, what kind of a program would you like to write? Would you like to write a kernel-based program, or something that is more pragma based, like in the case of OpenMP? And let's say you're happy with writing kernel style programs, then you can use DPC++, and if not, you can use OpenMP offload. And independent of which language you choose, at the end of the day, you will have to optimize for performance, and tools like vTune and Advisor will come in handy there. So this is the yes branch of the first workflow. And let's say the offload was not useful, meaning you saw negative projections. Then the next question to answer is whether you're interested in supporting multiple architectures. And if the answer is yes, then you might use DPC++ or OpenMP offload here. And if the answer is no, you might just use the plain OpenMP without offload capabilities, or a library like TBB in order to enable multi-threading on the CPUs. And again, at the end of it, whatever choice you make, you will have to optimize for performance. And for that, vTune and Advisor again come to rescue. Now, maybe you might have this question about, why if I see negative gains on the accelerator, I might still be interested in coding in DP C++. And one way to think about this is, let's say, you have an application that you would like to run on accelerators, but today's accelerators don't show positive gains, but this doesn't mean that accelerators of tomorrow might also do the same, and maybe there might be an upcoming architecture which might serve your application better. And so if you would like to future-proof your application or your coding efforts at this point, you can still code in DPC++, only use the CPU capabilities and run it only on the CPU, and yet you have the option of checking back if things would work in a performant manner tomorrow. Right, so that'll be one of the category of customers who might choose to code in DPC++, given that offload is not useful. I hope that helps. And there might be other scenarios as well. But for now, let's just move on to the next category of users, and that is those who are starting developing a new application today. And since they're starting off today, they don't have an application they can feed into Offload Advisor and see if offload is useful or not. So at this point, the very first thing to do is to think about what architectures that you would like to support your application on, and accordingly make a choice between DPC++ or OpenMP offload versus OpenMP without offload versus TBB. And again, the same flow continues for this category of users as well. And the third category is, if you're running applications, rather CUDA applications, and you would like to test performance on other GPUs like Intel GPUs as well. And then you do have the option of migrating your application to DPC++ through the compatibility tool, and finally optimize for better performance using the profiling tools we have. So this is like a single node workflow that you might have, and you might fall in one of these three categories, and roughly this is how you would think about interacting with the various WinAPI toolkits. And in the next slide, I just want to show the same in the context of a multi-node workflow. And what I mean by this is you have you're a typical HPC user and you have a bunch of interconnected nodes, and you would like to deploy your application more than a single node, right? So in that scenario, much of the single node workflow still stays, but there are some additional boxes, and these are cluster specific boxes. So one of the things that you would like to check is, if your application is scaling really well. If yes, then you're good to go. But if not, then you have to tune for MPI. And there are various tools that you can use for tuning. For example, the Intel Trace Analyzer and Collector, or ITAC for short, that we saw in one of the previous slides. We have our highly performant Intel MPI library. So a swap to Intel MPI itself can give you good performance. And additionally, we do have a bunch of tuners. Actually, we do have 4 tuning utilities within Intel MPI. So things like AutoTuner and MPA Tune Fast are the latest additions to tuning utilities, and anybody struggling along the tuning lines, I would highly encourage them to go through those tuning utilities and use them. So today, these are really nice low overhead tuners, and you can in fact use them in your production runs as well. So I would encourage you to check them out in case you're interested. And finally, if there are issues with your cluster itself and not your application, then we have Intel Cluster Checker that you might also have to interact with, or let's say your system administrators might have to interact with. And yeah, so this is how you would do it using the base and the HPC toolkit if you're a multi-node user. Okay, so now I would start off with the case study. So this is where we would really see how the tools that we saw in the previous slides really come into action. So we need an application for that. And the one that I've considered here is a heat conduction solver, which is based on the finite difference method. and it's a two-dimensional transient solver. So maybe if you're not familiar with the domain, it doesn't really matter for the purpose of this presentation, but the high-level details and the interaction with the OneAPI tools will still be clear, independent of whether or not you come from this domain where you understand the PDEs here. So that is not important. So let me just start off with the equation itself that we are interested in, right? So just a bit of a background here to this case study. So the case study here assumes that you have an application that already runs on GPUs, and all you would like to do is see if offload is going to be useful, and then make the necessary changes and get it running in a profitable manner on GPUs. And so if you go back to the single node flow chart that I was showing, so this will be the flow, the very first flow on top, right? So we have an existing application in C. And what it really encodes is this particular equation, which is the discretized form that results after applying finite differences. So looking at the compute, there are a bunch of cells or grid points. Let's call them cells for now in your domain. And let's say you're interested in a certain cell, which is the one in the center. And your aim is to evaluate a certain quantity, in this case temperature, in the cell. And the way the scheme is designed is it depends upon its upper or up, down, left, and right neighbors, right? So L, U, R, and D stand for that. And if you were to just look at the values in these cells in the previous time step and plug them into this equation, then you will have the current temperature in this time step. So that's how this equation is designed. And essentially the problem in this case that we consider, or let's say the domain, is essentially a square plate with consider a hole at the center. And these are the various conditions, boundary conditions that have been imposed. And the way these kinds of solvers work is, we run them for a certain time steps until the point that the solution doesn't change anymore, which is what is termed as convergence, and then look at how the temperature field looks like. And in this case, it's places where it's around the boundaries where you have gradients that develop, and at the end of the day we just want to see if these gradients are captured correctly. So that's a bit of a background about the real physics that is being solved in this case heat conduction. So the very first step, if you recollect in the flow that I was showing, was checking if offload is going to be useful. And for that, we had a tool called Offload Advisor, as I previously introduced. And how does this really look like in reality? I've just tried to capture the command lines for this tool here. So if you're familiar with how the workflow worked in Advisor, the very first step one always did was running a survey, which is where high-level details about the application gets collected. And then there is the characterization step where trip count data as well as the floating point operation data was collected. And then there is also this deeper analysis to do, that is dependencies analysis, to check if there are any of the dependencies that might prevent offloading, if any of those exist. And the final step is the real step, which is the projection step, wherein you exactly specify which GPU you would like to project for. And in this case, we have selected Gen 9 GT2 GPU, which is an integrated GPU that I have on the machine that I would use for the demo later. And when the projection step runs, it actually makes use of data from the previous 3 steps. And that's how you have to do them in the right sequence. At the end of running the projection, you get an HTML report which looks like this, and there is a bunch of information here, but I would just want you to focus on a few details for now. The most important one is what was the original time, so 4.37 seconds that this application took on the CPU alone. And then after acceleration, that is after offloading to GPU, it takes just 900 milliseconds, so less than a second. So if you look at it, it is 4.8 times speed up. And in this case, Offload Advisor says that 99% of the code is offloadable, and there are 11 sites to offload. And here is a list of all the offload candidates. And the top one is the most important one, which is because it is the most time-consuming loop. Right? So it takes 3.9 seconds, and after offloading, it is expected to take less than a second. Right, so these are the kinds of details, and please note that at this point, all we are feeding into the tool is a binary that runs on the CPU. So the code is not GPU ready. Neither does Offload Advisor do that for you. It just has certain models built in which are able to project performance, right? So not a real measurement, but just a projection. So that is what Offload Advisor does, and it is pretty accurate as well. Right. So that's the HTML report that comes out after you've done the previous step, which is running, survey, characterization, dependencies, and projection. The next step is to really make your application ready so that it is able to run on your accelerator. And in this case, you again have to make this choice about which kind of language you wanted to choose, or which kind of a programming style you wanted to have. So do you want to write a kernel style program, or do you want to write a pragma based program? So that's the next question to answer. And in this case, we went ahead with selecting DPE C++ as a choice. And what that really means is captured in the next 2 slides, right? So converting a C++ code into DP++, what does it really mean to do? So the very first step is to add the required headers. So these are just your typical include statements. Then you have the concept of a device, and that's where you have the CPU, GPU, FPGA, or any other accelerator. So the keyword for that is a device within these kinds of heterogeneous programs. And here we make a selection, and that is using this default selector mechanism. And what it really means is there is a certain ranking mechanism. So the runtime is aware of all the devices that exist on a particular node. And let's say if you have a Xeon and a GPU connected to the same node, then the GPU gets a higher ranking. And that is the one that gets selected by default for any offload. And if you would like to be specific, you have the option of using things like CPU selector or GPU selector instead of default selector here. And then we construct our device. So in this case, D is our device, and we use it in the next step while we are creating a queue called Q. And we may make a connection between the device and the queue here. So the device is passed as an argument to the queue, and queue is a means of connecting and communicating with the device as you execute your application. And then after this is done, you might want to check if your application selected the device that you wanted it to select. And for that, you can just print out the device info using the syntax shown here. And every time you run your application, then you know that you have been using the correct device. and interpret the results correctly from there on. So there's actually another step that comes before this, and that is memory allocation. And we have two mechanisms within DP C++ framework, and that is using either USM, that is Unified Shared Memory, wherein you're using pointers, or you have the second way of memory allocation, which is using buffers and accessors that I have used here. So in this case, using these mechanisms, you're able to interact or move the data between the host and the device. And the next step finally is expressing the parallelism, right? So this is essentially how you kernelize your code. And in this case, if I just go back to the one of the previous slides, you will see that Offload Advisor was suggesting that there is this evolve function which has the highest gain when offloaded to GPU. So what we really have done is we have focused on that same evolve function, and it really sits inside a time loop. So the same function runs again and again, so that you have that time stepping, as I was trying to indicate in the previous slides. So what we do is we retain the for loop over the time steps as is, but inside the loop we have our evolve function, which is really offloaded to the GPU using the parallel for method. So there are various ways in which one can do this. One can use either how we've used parallel for, or there is the possibility of using indie range, or there is hierarchical parallelism that one might use as well. So this is the simplest way to do things, and we've just gone ahead and used the h.parallel for method, inside which we invoke the evolve function. So this is like the most important step here in terms of getting your application offloaded to the GPU. The other steps are necessary as well, but this is really where we are putting the stencil operation, that 5-point stencil, upper, lower, left, and right values that I was showing you before. Now that's exactly present within this evolve function, and this is exactly the compute that we would like to do on the GPU as suggested by Offload Advisor. So with these changes in the original source, we now have a DPC++ code that we can then compile and target the GPUs through. For these kinds of details about DPC++ that I don't have the time to cover right now, you might refer to this really nice book on data parallel C++, which is available in the link shown on screen here. There is, several chapters. One is dedicated towards expressing parallelism and things like that. So you might find more details about these concepts here, as well as the USM and buffers and accessors that I didn't go into a lot of detail here. So you can find all of those details covered really well in this book here. And yeah, finally, moving on to the result slide here. So at the end of doing that porting effort, we are able to target CPUs, GPUs, and FPGAs through the same source code. We are able to use certain runtime controls as well as source level controls to really control which device we would like to really run on. Or which combination of devices we would really want to run on. And at the end of the activity, without actually optimizing the application, what we've seen is for 100 time steps and for a domain size that is listed here, right? So roughly 2,000 square, 4,000 square, and 5,000 square. We are comparing performance that we get on the GPUs versus the plain CPU baseline code. And you can see that in every case, we're doing slightly better. And yeah, the CPU of interest here was just a small Xeon E2176. And the GPU, like I pointed before, it's just an integrated GPU with 24 execution units. So this is also a small GPU, and our target GPUs are discrete GPUs, and this application will perfectly run even on our discrete GPUs. But for the purpose of this presentation, since our mainline discrete GPUs are about to be released, I'm unable to show those numbers today. But this still conveys the exercise that you have to go through to get your application running on the discrete GPUs that will come out soon. So some architectures that you might have heard of are PVC, Ponte Vecchio. These are our real targets, and the numbers for them, unfortunately, like I said, unable to share at this point. But that's where we will really see good performance, and the purpose of this slide was to just give you the feel for what you can experience today publicly on machines like the Intel Depth Cloud, which are hosting these kinds of GPUs. So I believe that's the next part that I would get into now. That is to walk you through a demo of what we just saw on the screen. Go on to the Depth Cloud itself, and in this case, I am already in the terminal. It's a web-based terminal based on Jupyter Hub, and it is on this machine called the Intel Depth Cloud. So, it's fairly straightforward to get access to this, and I have added links into the presentation, and I will perhaps share them in one of the subsequent slides. For now, let's just assume that, we have the terminal, and the first thing to do is get a GPU node. And the way you do that, well, this cluster is based on a job scheduler, and the command for that is qserp. Followed by a -i-l number of nodes. I just need a single node, type of node. I'm looking for a GPU node. And ppn equals 2 in this case means that I get both the sockets that are available on this dual socket node. And for this machine, you only have the option of exclusive access. So what that means is anything apart from ppn equals 2 will result in an error. So this is the only legal value you have on this machine. And if I hit enter within a few seconds, I should have a GPU node. So we do have the node now. And the very first thing that, is a good practice to do, since we're really interested in a GPU node, is to check that we really got a GPU node. So the command for that is clinfo followed by -l, so that it just will print the list of devices that we have here. And in this case, you see that there is UHD Graphics P630, which is nothing but the Gen 9 GPU that we were interested in. And you can now, at this point, run clinfo without the -l flag. And you can also confirm further details about the GPU here, like the number of EUs and things like that, the number of execution units. So yeah, this is the part we are interested in. So, we have a device which is our P630, and we will look for the max compute units, which is 24. So these compute units are nothing but the EUs or the execution units, and the correct number shows up. So we know that, yeah, this is the correct GPU that we were interested in. And similarly, if you want the details about the CPU, then there is this other command that you can also use, CPU info-g, which is just showing you what kind of a Xeon we have. Number of cores is 6, and hyperthreading is enabled, and it's actually a single socket machine, not a dual socket, as I previously stated. Right. So with this, the next thing to do is find our application. So here, this is the target folder. It's simple C, and yeah, it contains all the files that we are interested in. And I just want to run that. Okay. Right. So here, yeah, the first thing to do is, so this is, how we would start off. And this is an application that only runs on the CPU. It is not GPU enabled yet. So, it has a compile script. If I look at the contents of compile, it also makes use of the libpng library, and therefore is just exporting the libpng root, and also the library folder of libpng has been added into the LD library path variable. So that is just taking care of some dependencies. The main step is running make, and running make will invoke our make file. And I will just walk you through the make file as well. And inside here, the ICC compiler is being used, which is a classic C++ compiler. And then, we're switching on the O3 optimization and switching on the debug flag -G. So in this case, what I would really do is I would perhaps just maintain it at O0. Yeah, much of it is, a simple make file, so I wouldn't go into the details there. And at this point, I will just save and close it. And I would just check the version of ICC I have, just to make sure it's the latest, which it is. And I would just run make, perhaps remove the binary first, and then run make. Okay, sorry. So it cannot find the libpng, and that's because I should have run the compile script, which does the LD preload and the PNG root setting. Okay. And after this, I have my binary, which in this case is called heat MPI. And yeah, so we are ready to really run this application, and we will give it some arguments. So the first two arguments are really the domain size. In this case, we selected 2000 by 2000 grid points in X and Y. In reality, what that means is 2002 cross 2002. And then we have to give it a number of time steps. So I will just go ahead and say 500 time steps. So that's the evolution that it would do in time. And this is precisely the number of times the loop would run, the one that I was showing in the slides before, the time loop. So it says iteration took 4.795 seconds, so just under 5 seconds, and it is just printing the reference value of temperature at a certain location in the grid, and that is 53 degree Celsius. So fine, we have a code that runs on our CPU, and yeah, the next step is to figure out if offload will be useful for this particular application. And for that, we would run what is called as offload advisor, like we've already seen. And if I just bring back the presentation again, these are precisely the commands that you should be running, and as you might see, these are not trivial, the command lines, and it's hard to remember all the correct flags to use. So I just want to share a simple trick that you can use so that you generate the right command lines every time. And for that, what you could do is launch Advisor in your local Windows GUI. Right, so we are not on a Linux machine now. I'm launching Advisor on my Windows machine, and what I would do here is I would just start a new project. So let's just call it DevCon 100, create project. And I'm presented with the project properties dialog box. So the name of my application or name of my binary in this case is heat_MPA. So I give it that. Please note that I would not be running my application on my Windows GUI, but I'm just acting as though I will do that. And the real intention is to just get the correct command lines, right? So I gave it the application. This doesn't exist on my Windows machine, but anyway, I will still write it, and I will click on performance modeling because that is the step that I would really like to do. And on device configuration, I will hit Gen 9 GT2 because this is what we are currently interested in. I'll say OK. As soon as I do this, I will be presented with a bunch of analysis types that I can run on Advisor. So let's wait for that to load. It is here, and I would select offload modeling because that's really what I'm interested in. And I will hit choose. And let me just close this window. Right. So at this point, you will see that there are a bunch of selections to make. So something I did not mention before is there are various accuracy levels within Offload Advisor. So it goes from low, medium, high, and there is a custom one. So low accuracy indicates that the projection numbers might not be very accurate, but the amount of overhead will be really small. So if I click on low, you see the overhead just goes there. Medium is up to that, and high is it's really time consuming. And the command lines that I showed in the presentation were really for the high accuracy analysis. Now, for the purpose of this demo, to save time, we will just hit on low. And this was previously selected as Gen 9 GT2, so I'll let it remain like that. And then comes the real command line generation step, right? So for survey, for example, what I have to do is click on this arrow, and then there is this get command line button. So I have to click on that and then say copy, right? And then all I need to do is take this to my command line, and I just need to edit it slightly and run it as is. So instead of putting it here, what I might do is I might put it in this file. Right, the first part I can get rid of. I don't really need this path. It is not valid for my Linux machine. And similarly, the next part, project directory, is also irrelevant. So I don't need so much. So all that remains after that is heat MPI, right? So let's just remember that and hit this. I would just do advisor data 2. And that is my project directory, a new directory that I would like to create, followed by the name of my application, which is heat MPI. And then I wanted it to run on a 2000 by 2000 grid size for 100 time steps. So here is my command line, which is ready for the first step. So what I can do is I can just save, close. I can just cat this and yeah, just get it running right here. So it would print a bunch of things on screen, and at the end of it, we would have had a result folder. That is all we need. And like you see, Advisor really ran the application and shows the time it took and the reference value as well. And if I just do an ls, this is the folder that got created right now. And inside this are, certain files. It's non-empty. So that's all we need, and we can move on to the next step. So, you would do the same. You would come here onto the characterization step, which is the next step. and click on the get command line, and then modify this accordingly, and then run it for your application. So I have done this previously and have accumulated the command line, so we can just reuse them. But I just want you to see that you can generate. Let's say if you were to do a high accuracy analysis, then also the dependencies get ticked, which is not required for the low accuracy analysis. And then you can click on this, get the command line, and get going from here. Right. So that's one way in which you can generate command lines, not just in Advisor, but the same applies for other tools like vTune as well. So in this case, I have previously within steps.sh stored my commands. So we have already run this particular step. So I would go ahead and run the characterization step, and in this interface, if you want to right click and get the copy cut options, then you have to also hold Shift. By default, it just gives you this menu. So Shift, right click, paste, and we will maintain the same directory name. So what that does is it builds on top of the results that were collected in the last step. And at the end of it, again, you will see that it ran the application again and collected the trip count and flop data, and presents some information which is not really needed for what we are trying to do at this point, since rather than optimizing for the CPUs, we are running this projection step, right? So once this is done, then the next step is to really run the projection, and the way you do that is mentioned here. So I will just run this particular step, and in this case, just give it the name of the folder that I'm working on, and hit enter. So it has selected the Gen 9 accelerator with 24 EUs as the target device, and at the end it has generated an HTML report which is stored in a path that is shown here. Right. So yeah, this is, but keep in mind that this was the low accuracy analysis. So now what I would do is I would quickly show you how things look like when you do a high accuracy analysis, and that's stored here. So you might download it right from that interface, but since it's a low accuracy report, I want you to see the high accuracy one. It really looks like this, and you can hit the source view. So here you can see the source code also appears at the bottom, and the offload sites are listed on top, and quite a few other details which I don't have the time to cover right now. The most important detail is that we see a positive speed up number, and that's more or less what we're seeing in which regions to offload. Right. So with that said, what I would do next is get into my deployed machine, and here I do have the converted or the ported application in another folder, and like I was showing you before, okay, right. I think we have to get into main, and yeah, and here is where the time evolution comes in, where you have a time loop over evolve. And as I was showing you, we've used the kernel edge.paddle for method to submit or run the evolve function on the GPU. So this is important for that very first offload site being offloaded to the GPU. Right, so that's one. And in this case as well, let me remove the binary because it exists. Run the makefile as usual. And in this case, you will see it invokes the dpcpp command, and I made the same mistake again. So I hit make while I should be running the compile script so that the required dependencies are taken care of. And at the end of it, I have my heat or binary. And yeah, so at this point, I can go ahead and run the test cases of interest for us. So 2000 by 2000 by 500 time steps. And in this case, yeah, I'll just go ahead and hit enter. So the first change you will see is we are printing the device on which we are running. So P630, the GPU that was of interest to us, and it took about 2.2 seconds. Now the same thing I would run on a GPU. So the the same thing I would run on the CPU, and the way to change that using the runtime is to just set this environment variable cycle device filter equals CPU space, and then the same command that we were using before, and I hit enter, and you see that now it is actually running on the CPU. And yeah, the amount of time is roughly twice, right? So what completed in 2 seconds, 2.2 on the GPU takes 4.6 on the CPU. And yeah, so the same can also run on an FPGA using similar controls, but we don't have an FPGA node here right now. And I would like to just restrict the focus to the CPUs and the GPU story for now in this presentation. And so that's how, you see that the same source with just a different variable is able to offload to the CPU or to the GPU. So we've accomplished what we set out in our motivation right in one of the starting slides. That is, a single source code through this one API framework is able to run on multiple devices. And with this, I would like to end the demo and go back to the presentation. So hopefully you've got a feel for how this really looks like, the usage of these tools, and let's say the machine dev cloud, how things really work on that, and what really oneAPI is all about. So in closing, towards the end, I just want to also focus your attention on the priority support angle. So in the past, quite a few of the tools present in Parallel Studio were available only under a license and were not freely available. But as you would see in the oneAPI era, everything is available free of cost. The only thing that isn't included is priority support, and this is something that you can buy, and you also have the option of using community support, which is again available for free. But it is just the community supported scheme that's present there. And if your Parallel Studio, let's say you have the support with your Parallel Studio tool suite, you can very easily migrate into the oneAPI toolkits, and the same license will continue. The same is valid for System Studio, where you can use a combination of base and IoT toolkit to accomplish what you were doing before. So that's a very quick note on the support angle. And here are a few demonstrations. So we've already worked with quite a few of our customers worldwide, and we have quite a few success stories already with customers like Argonne Labs, ZIB, CERN, Bentley. These customers are already using oneAPI, and we also have some testimonials that you can see for yourself in the link that I've shown here. So you can see the customers speak about the kind of work they've done with us. And we have a catalog of 250 plus applications that were developed using oneAPI tools, and that is also publicly available to view in our oneAPI catalog. And so we come to the last slide, which is the summary slide. So here, just to reiterate, we started off by saying that we have a diverse set of workloads and they thrive on a certain hardware, and programming for those hardware is not often trivial. And so One API tried to close that gap by providing functional as well as performance portability across CPUs, GPUs, FPGAs, and other accelerators. And there is no vendor lock-in that happens in this approach. And you can be assured that your code that you're developing today will work on the platforms of tomorrow. And in the demo, you've seen it all in action. In reality, maybe your applications might be bigger, and you will use the same workflow, but just at a different scale. So with that, I would just like to thank you all for your attention. And if there are any questions you might have, please send me an email. And my email address was shared earlier. I can go back to the slide for a few more seconds and please write me any concerns or feedback or questions you might have. So with that, I would like to end this presentation and thank you for your attention and time. Thanks, everyone. Have a good day ahead.